Hoover High School AP Chemistry, this is Lesson 16 on Gas Laws 2. We're going to continue with some study of stoichiometry of gases and study some more of the gas laws. So we're going back to our original reference slide here of what we're doing. We're trying to get into a chemical equation. In order to do that, we have to have moles. We have to have a number of molecules because chemical equations match up numbers of molecules or atoms. Previously we studied grams, putting things on a scale and doing molar mass conversions. If you know the substance and you know how many grams of the substance you have, you can convert that into moles. In this unit, what we've been looking at is if you don't know the mass, but it is a gas, and you know the pressure, volume, and temperature of the gas, it will tell you how many moles of the gas you have using the ideal gas law. So that's what we're going to study in this unit right here. So we're focusing on this middle arrow right here using the gas laws, solving PV equals nRT for N, we can get the number of moles, and then we can work within the chemical equation. So the relationship between Boyle's, Gay-Lussac's, and Charles' law are as follows. Boyle's law says that pressure and volume are related. So if you change the pressure and volume before you make a change, has to equal the pressure times the volume after the change. That's what that equation is saying. For Gay-Lussac's law, it says that temperature and pressure are related in a similar way. And for Charles' law, it says that temperature and volume are related. Now, mathematically, those three equations can be put together, and they can be combined into what's called the combined gas law, and it's P1V1 over T1 equals P2V2 over T2. So as we move further into this course, unit of measurement cancellation will become more complicated. Use the principles of fraction division to cancel units. If two levels of a fraction have a common word, then the units of those levels can be canceled. So we remember we have a fraction has a numerator which is on the top and a denominator which is on the bottom. Now if the numerator is a fraction itself, then we can call that the numerator top and numerator bottom. And if the denominator is a fraction itself, then we can call that the denominator top and the denominator bottom. If there's only one level on either the numerator or the denominator, it's considered to be on the top. So we've done this before. We did this in class, so we're going to just practice canceling units here. Be sure you understand when you can cancel and when you can't. So we'll start canceling this. So Kelvin. So Kelvin is in the numerator top and the numerator bottom. So they both have the word numerator in common, so you can cancel those. Atmosphere is in numerator top and denominator top. They both have the word top in common, so you can cancel those. Liters is also numerator top, denominator top. And grams. Grams is in denominator top, denominator bottom. So they both have the word denominator in common. You could cancel those. Notice the grams that's in numerator bottom could have been canceled with the grams that's in denominator bottom. You would end up with the same final result, whichever one of those pairs you had decided to cancel. Finally, moles. Moles is in numerator bottom and denominator bottom, so they both have the word bottom in common, so they cancel. The two units we have left that won't cancel out are grams and liters. Now you have to remember that a fraction on the bottom of two fractions, you flip and multiply, just like they were numbers. So that means the liters, which is in denominator bottom, flips all the way up to numerator top. And then gram stays in the denominator there, and that's the final units that you would get from that problem. Okay, standard temperature and pressure is the temperature of 0 degrees centigrade, that's 273 Kelvin, and 1 atmosphere. 0 degrees is the freezing point of water. That might sound kind of cold, but compared to gases like hydrogen gas, oxygen gas, which freeze at hundreds of degrees below 0 degrees is not that cold for a gas. Of course, 1 atmosphere of pressure is the pressure that you feel here in San Diego at sea level. So using STP and the ideal gas law, we can determine a relationship between the number of moles and the volume of the gas. We can determine 1 mole of gas is equal to 22.4 liters. So let's go ahead and prove that. So you have PV equals nRT, you solve for V, and you set the number of moles equal to 1, And then STP is 273 Kelvin and 1 atmosphere. So let's see how you can cancel the units here. So Kelvin in the numerator top and in the numerator bottom cancel. Moles in the numerator top and numerator bottom cancel. Atmospheres in the numerator top and the denominator top cancel. So the only thing you have left is liters. And you multiply the numbers out and you get 22.4 liters is 1 mole is equal to 1 mole at standard temperature pressure. So that means 1 mole of any gas will equal 22.4 liters in volume at STP. Okay, so let's do a problem here. How many grams of H2O gas, it could be liquid, but we're going to deal with gas here, will be produced from the combustion of 12.4 liters of CH4 at STP? So you see up on the top you have liters, and you've measured some number of liters. You can fill in those blank boxes. And then notice that the units of conversion are the same for all of them. 1 mole equals 22.4 liters, no matter what substance you're dealing with, because it's always true for any gas that 1 mole equals 22.4 liters at STP. Down at the bottom we have what we've seen before. We have grams and we have molar mass conversions to get us in and out of the equation if we know grams. And we know the substance, what the substance is. So 12.4 liters, we start off in the upper left red box there. And then we come down through the moles to liters conversion to get us into the equation in moles of CH4. Then we take this across from moles of CH4 to moles of H2O. And then we need to get out of the equation for our final answer from moles of H2O to grams of H2O. So it's a 3 conversion problem. So we go ahead. Up in the upper left, you see up there at the very top, 12.4 liters of CH4 is where we start. Where we end up is some unknown number of grams of H2O. So our first conversion is moles to liters. 1 mole is 22.4 liters, or 22.4 liters for every 1 mole. Which one do you use? You use the first one because you need liters of CH4 to cancel out. So liters CH4 cancels liters CH4. And at that point in the equation, you are right there in that red box below CH4. It's 0.554 moles is where you are now. Again, you don't normally do these intermediate conversions in the middle of the problem. We're just showing you how this problem is flowing. Now we need to convert from 1 mole of CH4 to 2 moles of H2O. Which one goes on top? Which one goes on bottom? We need moles of CH4 on the bottom so that it will cancel with moles of CH4 up there. So moles of H2O is on top. And now that puts us over in the moles of H2O box in the chemical equation, 1.1 moles of H2O. Finally, we need to get out of the equation using the molar mass of 1 mole equals 18.02 grams. So there's your 2 choices. Which one do you pick? You put moles of H2O on the bottom. There it is. Moles cancels with moles, and you end up with grams of H2O on the top. So you do the math now, multiply everything on the top, divide by everything on the bottom, and you end up with 20.0 grams of H2O, and you can put that in the box down at the very bottom there. Okay, now let's do one where it's not standard temperature and pressure. So how many grams of H2O will be created from 28.7 liters of CH4 at 1.06 atmospheres and 290 Kelvin in temperature? So the conditions are not STP. For this problem, we can compute the number of moles using PV equals nRT. So we solve for the number of moles, so there's the original equation. And you're going to solve that for n. You get n equals PV equals R over RT. So now we just plug in the numbers. And there they are plugged in. Now cancel your units. Atmospheres on numerator top cancels with atmospheres on denominator top. Kelvin at denominator top cancels with Kelvin and denominator bottom. Liters in numerator top cancels with liters in denominator top. And the only unit you have left is moles. So you do the math on that and you get 1.28 moles. So now we're going to plug that into the equation. So we come over here, and there's the same equation we just finished. Now we already have moles. You don't need to do any conversions. We actually just did the conversion. So you go ahead and you can plug that directly into the equation because it's in moles. So it's 1.28 moles. Now we have to do the conversion from moles of CH4 to moles of H2O. Well, there we go. We're showing the path here. Okay. Now we're going to convert from moles of CH4 to moles of H2O. And there's the two choices you have. 1 mole CH4, 2 moles H2O. Same one we had the last problem. So which one do you put up there? You put the one with moles of CH4 on the bottom so that moles of CH4 cancels with moles of CH4. And now that puts you over in the red box underneath H2O. It's 2.56 moles. Now we're ready to come out using the molar mass conversion of moles to grams. Which one do you use? Same one as last time. And that's going to put moles of H2O on the bottom so they cancel. And you're left with grams of H2O as the final unit. And if you do the math, you get 46.1 grams of water. Okay, so now we know another way to get inside a chemical equation. If it's a gas and we know the pressure, temperature, and volume of the gas, we can convert that to moles, and moles is always the key to getting inside of a chemical equation. Okay, now we're going to introduce a new concept, density. The gas density is the mass of the gas divided by the volume it occupies. It's actually the math, that's the general definition for density of anything. It's the mass of the substance divided by how much space it takes up. Okay? So, if you have a big ball of cotton, that has a bigger volume than a little tiny steel ball, but the mass of the steel ball is compacted down into a much tighter volume, so it has a greater density than the cotton. Okay, so here we have a single hydrogen molecule. There's one hydrogen molecule, gas molecule, in this volume. So let's say this is a mole of hydrogen. This molecule represents a mole of hydrogen. So that would be 1 gram of hydrogen, and let's say the volume is 1 cubic meter. And so it would be 1 gram per cubic meter. Now if you put a second hydrogen in there, it's now going to be 2 grams per cubic meter. You've increased the mass and kept the volume the same. So therefore the density is greater. And the density can also be increased when the volume is decreased. So you could have squeezed those down. You could have had a single molecule of hydrogen and then squeezed the volume down, made it smaller area. That would have increased the density as well. So density is mass over volume, abbreviated small d equals m over v. Sometimes density uses the Greek letter rho to designate it, but we're going to use small d. So molar mass of a gas can be determined if its density is known. So let's start with the equation PV equals nRT. I'm going to do a derivation for you. Just follow it, but you don't have to know how to do this. I won't test you on this. So if you take that equation, you multiply both sides by m for mass. Remember, we measure mass in grams, but that's mass. Okay, now we're going to do several divisions at the same time. You're going to divide both sides by moles, by volume, and by pressure. And then you're going to group the m and the v together over on the right-hand side. So you see the equation on the bottom? That's after you've done all of those things that's just stated in number 3. So what happens? What do you have there now? Well, m over n is moles is grams in its mass. It's mass per mole, or grams per mole. And grams per mole is what we call molar mass. It's how many grams in a single mole, in 1 mole. Mass per volume is what we call density. So we can then rewrite the formula like this. The molar mass, that's the mass, the mass over the number of moles, grams per mole, is mm, molar mass. And then the mass per volume over on the right-hand side of that equation is d, it's density. So you have molar mass equals density times R times T over P, where mm is molar mass and density is measured in grams per liter. Dalton's law of partial pressure states that the pressure of a mixture of different gases in a container is the sum of the individual pressures of the gases. So if you have a bunch of gases at different pressures, you can just straight up add up the pressures, and that'll give you the total pressure in the container. It kind of makes sense. If we think of pressure as how many times the molecules hit, then you can just simply add up how many times the molecules of different gases hit the side, and that'll be the total pressure. So P total, pressure total, equals P1 plus P2 plus P3. P1 could be the pressure of oxygen gas, P2 could be the pressure of nitrogen gas, and so on. If the gases occupy the same container at the same temperature, then pressure is directly related to number of moles. So if you look at that equation, R is always a constant. If we assume that the temperature is constant and that the volume of the container is constant, then that means the only thing that can vary is the number of moles and the pressure. So if you double N, you double the number of moles, you're going to double the pressure. And that makes sense because you have twice as many molecules hitting the sides of the container, so the pressure is going to be twice as much. And the same would be for other gases. The number of moles is proportional to the pressure of the second gas. The number of moles of the third gas is proportional to the pressure of the third gas. Okay, the ratio of the moles of a specific gas in a container divided by the total moles of a gas is called the mole fraction. So there's the formula for mole fraction. That letter that looks like an X is actually the Greek letter chi, C-H-I. And so what it's saying is if you have a gas N1 and you want to know what fraction of all the gases it is, you just take the number of moles of N1 and put it over the number of moles of all the gases. Let's just assume we have just two gases here. So you put it over the number of moles of N1 plus the number of moles of the other gas, N2, and that will give you the fraction of all the gases that are N1. Since the partial pressure of gas P1 is proportional to its mole fraction, then if you know the total pressure of the gas and you know the mole fraction, you can figure out the pressure of a specific gas. You know the mole fraction of that gas. So, example, a container holds 2 moles of O2 and 1 mole of H2 gas. What is the partial pressure of O2 gas if the total gas pressure is 960 torr? So find the mole fraction of O2 and multiply it by the total pressure. So there's the formula. So we said that the total gas pressure is 960, and the mole fraction for oxygen is going to be 2 moles of oxygen over 2 plus 1 moles total in the container. That's 3 moles total. So that would be 2/3. So 2/3 times 960 is going to equal 640 torr. Okay, kinetic molecular theory. Gases consist of large numbers of particles that are in continuous random motion. So they're not sticking together. They're not, they're just moving around freely. The combined volume of all gas particles is very small compared to the volume of the container. So they're not squeezed together. If the container is too small, then they starts to squeeze the gas particles together, and that could turn them into a liquid or even a solid just by squeezing them together tightly enough. The attractive and repulsive forces between gas particles do not exist. This is the main characteristic of a gas. Gas particles are separate from each other. We'll get into a subject called intermolecular forces, which talks about how and why molecules want to stick together, why they're attracted like little magnets to each other. But with gases, we assume that there are none of those forces. They have enough energy to keep them from having those attractive forces. Or the attractive forces are there, but they're overcome by the kinetic energy. Energy can be transferred between gas particles, but does not increase or decrease. If you've ever seen somebody play billiards or play pool, where they hit the ball with the stick and it hits another ball, the energy just immediately transfers from one ball to another. It makes a clicking sound, and that's what molecules are thought to do. They don't squeeze together. They don't compress. It's not like two rubber balls hitting each other. It's like two very hard balls hitting each other, and they just click off of each other. Finally, the average kinetic energy of gas particles is proportional to the absolute temperature. This means that the temperature in Kelvin, which is the absolute temperature, reflects the average kinetic energy. That's what we said temperature means. It's the average kinetic energy of the molecules. Okay, root mean squared. You'll come across this in science oftentimes, and it's used to calculate the speed of gas molecules. It's called the root mean squared speed. So what is the average velocity and RMS speed, root mean squared speed, of the two particles below? So here come two gas particles. There they are. Okay, so we stopped them so you could see them. So you have one of them moving to the right at 10 meters per second and one of them moving to the left at 10 meters per second. Now, when you're talking about a vector, velocity, you're talking about a vector concept. It has a direction to it. So the particle moving to the right, we've just assigned a positive value to its velocity. It's moving positive 10 meters per second because it's moving to the right. The one moving to the left is therefore negative 10 meters per second. It's not inferior to be a negative. There's nothing inferior about being negative. It just means it's moving in the opposite direction of the positive. So they're moving in opposite directions. So you don't say right and left. You assign them a plus minus value. So moving to the right is positive, moving to the left is negative. So what's the average velocity of those two? Well, you take the 10 meters per second to the right, you add to it the 10 meters per second to the left, which is negative 10 meters per second. You divide by 2, that's the number of particles, and you get an average velocity of 0. Now that might seem funny, but that's the way velocity works. Even though those particles, we're assuming they're continuing to move right and left right now, they have no velocity because it cancels out. The average cancels out. The plus and the minus cancels out. So it is possible to have 0 velocity when you move. If you run around the track at Hoover High School 1 full lap, your average velocity is 0 because you didn't move anywhere from where you started. You ended up right back where you started. So you had no vector component to your movement. You just ended up right where you started. Okay, so this would be 0 for the velocity. Well, we don't want it to show 0 because obviously that's kind of misleading as to how fast they're moving. So we want to deal with speed. Speed does not care about direction, so there's no plus and minus signs. So they use RMS to get you there. So for RMS speed, we square the velocities, take their average, and take the square root. I always think of it as you do it in the opposite order of the name. It's called root mean square, but the first thing you do is you square, and then you go back and you take the mean, and then you go back one more and you take the square root. So root mean square, really the way you do it is square, mean, root. So let's see that. So we take our two numbers, 10 and minus 10, we square them. That gives us positive 100 in both cases. So then you add them together, you get 200, you divide by the number of particles, which is 2, and you get 100 meters squared per second squared. And now you take the square root of that, and that gives you 10 meters per second. And as you can see, they really are both moving at 10 meters per second, so it's more accurate to speak in terms of RMS speed than it is in terms of velocities. Okay, so again, you square the numbers, you take the average of those squared numbers, and then you take the square root of that average, and that will give you the RMS speed. So velocities have a directional component and cancel out. That's because they're vectors. The RMS values only account for speed and not direction, and that gives you the average speed. So previously we mentioned Graham's law of effusion, which indicated the relative speeds of two particles. So the speed of the lighter particle compared to the heavier particle is mass of heavier over mass of lighter, and then you take the square root. In our example in the previous video, the mass of the heavier was 8, the mass of the lighter was 2. So 8 divided by 2 is 4. You take the square root of 4, you get 2. That means the lighter particle is moving twice as fast. It doesn't tell you how many meters per second it's moving, how fast it's moving. It just tells you it's moving twice as fast as the heavier. So now we're going to have a formula here. The formula for the actual speed of gas particles in meters per second is this. It's U, which represents speed, equals the square root of 3RT over the molar mass. So U is the speed in meters per second. So the average speed of some common gas molecules range between about 300 to 3,000 meters per second at room temperature, 25 C. So air is made up of oxygen molecules and nitrogen molecules. You can see those. Those are the two highest curves. And those are right around somewhere under 500, 5 times 10 to the second, 500 meters per second. So they're both about the same mass. They're next to each other on the periodic table. And they're right around the same speed as well. So air consisting of N2 and O2 molecules which have about the same mass and speed. And the graphs to the right shows the fraction of common gas molecules at various speeds. Diffusion is the random movement of gas particles in an open space. So if you see the container on the left, it's just a container. There's nothing in it. It's just the gas particles move around freely, and that's called diffusion. Effusion is the movement of particles through a small hole. That would be the gas container on the right. They start off in the left-hand side of that gas container, the effusion one, and they go through that little hole where the arrow is showing, and they eventually go over to the other side. So the purpose of a fusion is it's a laboratory process that allows the speed of gas particles to be measured because it focuses them into a known space. So you can actually measure how many particles of the green and purple gases you're getting over in the right-hand side after a certain amount of time, and you can determine how fast they fuse in relation to each other. Mean free path is the average distance of a gas particle travels before colliding with another gas particle. Okay, now we're going to talk about what if they're not ideal gases. In the real world, gases don't always come close to ideal gas behavior. So how do you deal with that? So ideal gas behavior does not perfectly exist in the real world. Ideal gas particles are not interfered with. They move freely. So gases behave most like ideal gases when the temperature is high. This is because the particles have enough kinetic energy to avoid being attracted to other particles. They can overcome those intermolecular attractions to each other and just fly apart from each other. So high temperature means that the gas behaves more like an ideal gas. On the other hand, if you don't have high temperature, this one on the bottom, those gas particles don't have very high temperature. However, they have low pressure. You notice there's not as many gas particles in that container. So pressure is low. This is because the particles are spaced far enough apart to avoid contacting other particles. So they tend to not get in each other's way. So the two things that lead to more ideal gas characteristics, the characteristics of an ideal gas, is to have them at high temperature and low pressure. Okay, van der Waals equation makes a correction for the fact that gases under high pressure and low volume, which increases pressure when you squeeze the volume down, it does increase the pressure, do not behave as ideal gases. So van der Waals equation is, and there it is. So you see it's the ideal gas law, but it has these terms added on here. N squared A over V squared and NB minus NB. So what do those do? A is a factor that represents the strength of the attraction between particles that makes a gas behave less ideally. So A is a factor that's taking into account the fact that they do have intermolecular forces that attract them and make them want to stick together. B is a factor that reduces the volume, which increases pressure. So if you take the volume there, V, and then you subtract something from it, it's as though you're making the volume smaller. So making the volume smaller effectively increases the pressure as well. So the key is this to understand. You don't really have to understand the details of this, other than, in summary, larger values for A and B means that the gas behaves less like an ideal gas. Okay, so that takes care of this really lesson, the unit on gas laws. And we're going to practice these throughout the year. You're going to come across these. We're going to get into solutions next, and how solution chemistry, that blue beaker you're seeing on your screen right now with the little guy on top of it, that would be an example of a solution. And we'll be talking about how to deal with solutions in chemical equations. Okay, so we'll see you in class and in the next video.